Well, hello everyone. My name's Michael Murray. This is my first time at BTS, and I'm honored to be here. I'd like to thank the organizers, and in particular Dr. Irina Rossi, who I don't see here, who invited me and told me of the conference to present my findings of what is a low-cost, relatively versatile, small form factor ULS 200 underwater laser scanner, and this is emergent technology that I came across in 2014 when I was invited by 2G Robotics to test their equipment with regards to submerged cultural resource management, maritime archaeological research, and submerged cultural resource management in mind. This is a device that's used primarily in the oil and gas industry, but it's pioneering and has pioneering potential for maritime archaeological use. This is the subject of the scan. This is the ULS, This is the ULS 200. As I said, small form factor. It's about 30 centimeter by 30 centimeter, weighs a little over 1 kilogram in the water, ballasted, so very light, can fit on a lot of different platforms, vehicle platforms, including ROVs and AUVs. That will hopefully be explored at a later date, but this is a diver deployed option that we're testing in shallow water contexts. Just a few notes before I get started. The presentation called for scanning of the Nalic here in Croatia, but we didn't unfortunately have time to do that. However, we were able to scan a Roman shipwreck, which you'll see as one of the case studies involved with this, along with others in baseline tests. Also, I'm going to be briefly going over what a model is, talk about point clouds, meshes, textures as part of a 3D model. I understand many of you might not know what that is, but you can feel free to talk to me after the presentation. Also, we have a demonstration of it later today at 3:30 to 6:30, talking about more of its operational capabilities and how it may actually be of use to any of you guys who are considering high-definition 3D models for your tasks to accomplish your objectives. So with that, a little bit about me. Through the University of Southampton and their PhD program, prior to entering that in 2014 and starting this study, I have over 22 years of maritime archaeological experience, starting out, as many do, as a scientific diver for two of the largest submerged cultural resource management companies in the US and in Europe, in Pan American Consultants, and at Wessex Archaeology in the UK. I've also worked with the full range of standard remote sensing from side scan sonar to sub-bottom profilers to magnetometry. And then most recently have had the really distinct privilege of working with some of this cutting edge technology, 2G robotics, and also subsea LiDAR, which I wish I could get into and compare as a subsea metrology solution in the oil and gas industry since 2017. So with that, basic outline of the presentation, the way this will go is we're going to discuss first the motivation for use of this type of modality of 3D capture in a submerged cultural heritage and maritime research context. We'll go over a brief description of the ULS 200 and its operation, case study results from experimental indoor laboratory tests, marks the first case study, in order to achieve baseline of operation, because little is known outside the industry as how this really works and what its limitations and advantages are. Case study results then off in open water on the Mandalay shipwreck in Biscayne National Park off of Florida, in shallow water about 3 meters. And then, as I mentioned before, just a few days ago, with Dr. Irina Rossi's and at her invitation, we were able to conduct some scans of a 1 to 3 century AD Roman shipwreck in Croatia, followed by tentative conclusions, desired future testing, and some of the developmental potential will be discussed. So we live in this exciting era, I think, as many of you marine engineers know, where we're experiencing really exponential development of advanced computing systems, and the exponential development of that also has an inverse cost depreciation value where they're also becoming less expensive. So we're able to do more with less, and with sonar, with sensor technology, that also is consistent as well. So where laser scanning was big, bulky, expensive, only relegated to deep water sites, which you'll see a little bit later on in Dr. Rodrigo's presentation, which I'm really looking forward to later today. You can now use this and get similar quality in shallow water aspects. This is really kind of unprecedented times that we're in as far as being able to scan in high definition and really reinterpret or re-examine our history in novel ways. When you use underwater laser scanning, you're going to see that we have reflectivity values, which open up a whole other level of perception of a site that wasn't available before. And I'll discuss a little bit about that more now. But it's exciting because we can form these new understandings of human history and then also preserve the remains that are there. The best context by which to underwater laser scanning and its efficacy of use is to compare it with the advantages and disadvantages of the two other primary modalities out there, namely sonar and photogrammetry. Sonar has been, of course, side scan, been popularly used since Dr. Harold Edgerton and Dr. Martin Klein used it in the 1960s, but 3D, namely multi-beam sonar, has been utilized very recently in a landmark case study by Chris Sabick, my friend from Lake Champlain Maritime Museum. You can see this is of a barge, Lake Champlain Maritime, or Lake Champlain, in about 20 meters of water. Looks really good, looks really detailed from an overall standpoint. But what I want to express is that as much as this can scan in places like silty water and get overall good renditions, the details, of which the maritime archaeologist is often very interested in, it can be a little distorted and left wanting. In this case, in this particular case, there was a sketch of what are called hanging knees here, and there's some major distortion and even gaps, significant gaps in the data from these significant features, as opposed to, like I said, the sketched rendition. In the case of photogrammetry, in the case of photogrammetry, we've had also a real fervor and a real adoption of multi-image photogrammetry, low-cost stuff. It's great. We've been able to scan a whole bunch of sites and portray real nice, vivid renditions of them with true color. And that includes some of the work from McCarthy and Benjamin, as well as work by Dr. Irina Rossi and Kota Yamafune of a local shipwreck here, the Nalich, which has been recently released, publicized in 2019. But what I want to talk about is, as good as some of those are, the proliferation of all this means that in combination with the fact that we don't have standards of recordation, we don't have an accepted methodology for these new 3D technologies to be able to account for quality, anyone right now in submerged cultural resource management and maritime archaeology can upload a site and call it great, call it really good quality. But what I feel laser scanning can do is it can kind of shore up the lack of quality, and even more nefariously, photogrammetry, and sonar can do this, but photogrammetry can kind of render a smoke and mirrors type of effect. So what I mean is that the point cloud, which is the first point of the build, can look really good, of the shipwreck, for example. But if you build it to the mesh level, it can show the real, the melted chocolate effect, as my colleague and friend Pat Tanner shows, at the mesh. So the geometry, if that's what we're interested in the shipwreck, which is what a lot of maritime archaeologists are for true renditions of it, is worthless. So we need to to understand and know what's being published out there and what level of quality we have. And it extends, unfortunately, this lack of quality to major agencies. And in the US, we have the Bureau of Ocean Energy Management, which does great work. Recently, they've used the Okeanos Explorer, one of the best survey vessels to be able to, submersibles, to be able to go down and scan shipwreck sites in the Gulf of Mexico. This is the Monterey shipwreck. And they've done a good job at annotating and being able to, you can go to this website and look at the different features. But what I noticed, which was kind of glaring, was you have this claim that you have high resolution and high quality data of the site. And yet, what you can see here, starting if you look, are major sections of this wreck, which look like Swiss cheese. And I didn't know iron could float in water, but that's what is portrayed here. And is that the acceptable standard that we want to have in maritime archaeology? If we were doing sketches, if I was an illustrator for Dr. Rossi, and I was doing this by hand, and I sketched that out, I don't think I'd be an illustrator for very long under her services. So this is the kind of thing, the context I'm talking about, where laser scanning might be able to couple and work really well with laser scanning to shore this up, enhance the quality to where the fusion of these sensor technologies can enhance our understanding of what is there. So by contrast, this is in 2013, Monahans Shipwreck, laser scanned, really first full laser scan with a ULS 500 Sonar, laser line scanner, showing some of the remarkable detail that you can render without holes at the point cloud level, without distortions, if done properly. And of course, we'll talk about the limitations of where you can use this and where you can't. But of particular interest also is this what's called scalar value reflectivities, which kind of like similar in sonar, where you have backscatter and you can gain information from the site. Well, laser scanning, unique data set, when it comes to wondering about the condition of a site, which is of keen interest for preservation, in this case you can see little inclusions of marine boring organisms that have shell in them. And so this can be quantified, and quantified in millimetric terms. So that's really exciting aspect of underwater laser scanning if employed. However, like I said, there are challenges, and one of them is that the big one that we're all aware of is the ocean is diverse. Aquatic systems are diverse. Jules Jaffe says it very aptly that we have a myriad of particles and changing conditions in the environment that make it very challenging for any optical-based system, including laser scanning, to work in. So testing should be required, is something that I have sought in these different environments to gauge those limitations. Other challenges include deep water access. Of course, we're pushing the boundaries of that with ROV and AUV technology, but it becomes severely limited when we know that by human interpretation, when you have a human on the site, you can kind of guarantee certain things, but now we have a reliance beyond the 60-meter depth, which is the commercial and scientific compressed air limits. There's much more of the ocean of that, and we have to completely rely on these sensor technologies to interpret the site for us. Additionally, there's over 3 million estimated sites by UNESCO and by NASA. 3 million shipwreck sites that are yet to be discovered. And so there's a huge data set out there to be recorded. And for each material that is uncovered, then we have a responsibility as maritime archaeologists to uncover it. So this is a growing data set as advances in ROV and AUV detection continue. Constricted underwater geographic locations. I know we talk a lot about the oceans, but there's a vast amount of submerged cultural resources that are located in places like caves, submerged cave caverns. You have the karst system here in Croatia that I know I'm not very well aware of it, but must have cultural resources in it. So we need small, versatile mobile solution to be able to get to those and perform standards of recording that we're used to and that achieve modern day standards. Back again, and then lastly, we have cultural heritage is non-renewable. It's always degrading. There's entropy that's involved. And additionally, with the recent climate change crisis findings, the ocean acidification, rising ocean temperatures are rising at even more rapid rates. And what this means is that areas like the Arctic, near, say, Svalbard, which was told to me by Dr. Øyvind Odegaard of NTNU, we're now seeing marine-boring organisms entering and destroying the resource at as deep as 100 meters in these cold waters. So no longer do we consider those safe. Everything's kind of open to mass degradation. So the research questions then follow. When presented with an emergent deployable mobile technology of this relatively small form factor, how can this means of capture contribute in real terms, quantitative and qualitatively? How can it contribute, or how can it effectively work with other modalities of capture, like mentioned, photogrammetry and sonar, to enhance our interpretation of a site? How can these contribute all to the preservation? How can it further be innovated to become even more versatile and more powerful tool, not only within maritime archaeology, but across industries as well, potentially, in marine biology, marine ecology? We'll touch upon that a little bit later. What kinds of cross-disciplinary potential does it have in marine science? So the ULS is as I mentioned before, it's a rather small, nice, light, robust system housed in this titanium casing. It's composed, very simple, it's composed of an emitter, sends out 480 laser line points in a line which tracks over the subject being scanned and received by a sensor, which is essentially a high-definition camera. It can scan in the horizontal, along the horizontal plane, or on the vertical, with a 1 millimeter footprint for scanning resolution. It's deployable, as I said, by diver, primarily with an RS-485 connection. However, there is an adapter for RS-232 for ROV and AUV use, but this has not been tested before. I'm really excited about potentially being able to integrate this on a small to medium range ROV or AUV in the future with anyone out there who might like to talk to me about it. The cable layout, very simple. 4 diver deployed. This is the scanning head. 60-meter cable at max, goes to a simple junction box, converts 120 to 240 VAC to a 24 VDC, a USB connection, right here, and a simple laptop can collect the data from wherever your data collection point may be established. So this is a pretty good video of how the laser scanner works. Again, it's a laser line, and it's working in one of these cenotes, which I mentioned before, tracks along the subject. Usually what it is it's a triangulation scanner. So the scan area is dictated by the range. So in other words, the range is 0.38 to 2.5 meters. So if you scan at a half a meter, you're going to get a half meter swath, 1 meter, a little over 1 meter swath, and so on. At present, it's a static scanner. It must remain stable. It's not dynamic, but we'll talk about how that may be used in a more enhanced way. Known operational considerations or limitations: if there's excess silt in the water, turbidity, there is an algorithm by which to filter it, but for the most part, it isn't really very effective at collecting in turbid waters. Excess amount of ambient light, you have to scan really kind of at night or right before sunset. Highly reflective surfaces can really disrupt the scanning quality, and all of this is known on a qualitative basis, but again, to quantify these is part of the aims of this study. This is an example in Porkala in Finland. in July, where they used an aluminum skeleton cube. And aluminum is a common survey deployment technique, which is great for photography and great for sonar. But what this does is it bleeds over in laser scanning, disrupts the geometry. So we're looking, if we're employing this, we're looking for a new means of referencing, creating a new referencing and metrology system, which is part of what I'm working on as well. So baseline experiments, we start with the first case study. The objectives were in 2G Robotics' facility to obtain familiarity with the ULS operation in general, test the ULS in a controlled ambient, non-ambient, dry, and submerged scanning conditions by scanning a representative number of artifacts that you might find on the site, and experiment with a set of theoretical materials that would act as references for the determination of spatial accuracy, as that is always of interest. So in 2014, November, went to cold Waterloo, Canada. I don't advise it. It was we had to use the city water to jump in there. It wasn't heated. Had to use dry suits and stuff. But we scanned an assemblage of again, wide variety of artifacts, and they ranged from including the placement of these reference objects, including granite cubes and Siki disk, at different ranges, 1 meter, 2 meter, 3 meter, 4 meter ranges with the 500. The 200 wasn't available at that time, but the artifacts ranged from pottery, standard stoneware, from the University of Southampton, by the way. Dr. John Adams donated them generously, to bone, to wormwood, because wormwood, those have millimetric 1, 2 millimeter holes in them, so to be able to quantify that could be of real interest and use for the invasive nature on shipwrecks, to highly absorbent rust metals, as well as bright metals and finer features of objects to be scanned. So the results of that, well, we achieved again a negative rendition, which we expected in standard lighting, just absolute noise from the point cloud. In a non-ambient environment, completely changed. You have some nice detail, especially of the Siki disk. This area actually was too close. It was too close. The scanner was too close to get it, but the rest were pretty good. This mask had some high detail associated with it. What was of interest was, again, the degrading of the resolution as you would progress outward. So at 2 meter, a little over 2 meter range, you did have considerable less resolution, but also notice, at 300 megabytes, it's manageable data as well. It's not quite like what a lot of people think is laser scan data is in the gigabytes or tens of gigabytes range. You can work with this, but there at 3 meters and 4 meters, you see it with the same settings. There is a considerable drop-off in the resolution quality. You can't quite see it. This is a bad slide, but those are laser lines of the Siki disk showing the vertical resolution quality. So the distance between one line up here and one line down there, and that's 1.5 millimeters of res at the 1 meter mark, and then at 4.15, 3.7, it jumps to 3.7. So there is a significant diminishing factor of returns as you go out, scan outwards. But the detail, again, is noted within this matrix, and by using the references, we had only 1.7 millimeter of spatial error, which was great. But additionally, you can see teredo worm sizes measurable. Can't do that really with a lot of photogrammetry, maybe with a few sets. Sonar, definitely not. And then here are the reflectivity values. So here's a silver coin, polished, versus copper coins, which are oxidized. So you can scan a site, you can differentiate different materials, which is kind of exciting to me. I know this guy's fallen asleep over here, but I love this kind of revelation, and it can be of great diagnostic use for understanding the preservation quality of site. Wet laser scans were also conducted. They were similar. Sometimes you can see things in the laser scan data that you just simply can't see in photogrammetry and sonar. In this case, it's hard to see a 1 millimeter crack by photograph, but there is a 1 millimeter measurable crack with the laser scan that you can see. The cubes were used as references. Again, this allowed for metrology, good metrology of the site. So photogrammetry, very quick compared to laser scans. You can see that even though the Seiki disc, which has a plastic surface, somewhat reflective, had a really hard time. You get demonstrable holes here in the photogrammetric comparative rendition, along with lots of little artifacts that you have to clean up. So there's a lot of massaging of the data that you have here with photogrammetry that's needed. Sonar, in this case, we used a BlueView 5000. But what we discovered is within this constrained space, it was just a flexible tank, 1 meter depth for these artifacts to be in. There was a lot of multipath resistance, so it was useless. So what that means is also with this high-grade sonar, you can't use it inside the hull of a shipwreck to scan. You're going to get too much noise, or maybe within a restricted cavern system. So there's a limitation to that, even though it can scan in silt and produce wide area swaths. So the second case study, Mandalay Shipwreck, which is a steel-hulled schooner off the coast of Florida. It has a maritime heritage trail associated with it. This is one of the hallmarks of it. Wrecked in only 3 meters of depth, clear water and coral reef. Up to that point, there had only been some LiDAR, some early LiDAR renditions of the overall site, just showing the general geomorphology of where it is located, but no sonar, no photogrammetry of it, so it presented a case to be able to get a great recording of it. With the ULS, we use photogrammetry, again, as a comparative analog. 244 photos with a D300 camera and an aquatic housing. So we used the best, one of the best that multi-image photogrammetry can produce. Again, did the same thing, put out metrological references to ensure spatial accuracy. Of interest in this, you have very fine seams that separate the planking. And then you also have this soft coral, which is actually waving in the intertidal medium of this particular environment. And then you have thin linear, this is a rusted portion that held the bowsprit in for the shipwreck. Wanted to see how those features came out. So what ended up happening was what's of interest to underwater laser scanning is it really takes a fine eye, and it has a very narrow bandwidth of operation when it comes to the beam intensity value. Beam intensity is one of the key factors by being able to resolve these types. So you go through a calibration process. We started out 30%, 20, dropped all the way down, but you can see just a deviation of 1% versus another made all the difference in getting a quality scan. These are histograms showing the scalar value, intensity values. What you want is something of a parabola where you have greens and yellows in a Gaussian curve, in a nice Gaussian curve for a good quality scan. So again, I guess it doesn't show up very well. It shows up great on my laptop, but what you have, which is unprecedented, is this is the soft coral, and these are 1 millimeter diameter strands, slightly brachiated strands, which are resolved and measurable. No, the photogrammetry and sonar definitely could not achieve that. So that was a nice, outstanding thing, and it was in flux, so it caught it also in midstream, which was impressive. We measured ambient light, quantified it through a data hobo logger, and temperature as well. So again, the quantification of this was highly desired. And the results are that at over 1,000 lumens, which is what the sun produced, no good. Again, once again, for the laser scan, photogrammetry was fairly good. Had some artifacts and things to clean up, but pretty good. Can do that in daylight. And then at night, with 0 lumens at 12% beam intensity, we got the ideal laser scan. Speed, note the speed, 15 minutes to complete this photogrammetry, whereas it took only 2 minutes and 36 seconds to get the same rendition, which is about 1 meter by 3 meters overall, okay? So laser scanning can be very fast acquisition, which is an advantage. Combining the two proved to be just as interesting as well. The laser scan was able to scale constrain the photogrammetric record nicely and show what the spatial accuracy deviation of the photogrammetry was to the laser scan. So we had an error, again, a determined error of just 1.79 millimeters for the laser scan data set, plus minus. And the photogrammetry turned out to have a deviation of 2.5 centimeters over just the 1 meter by 3 meters for spatial accuracy. So this might be fine, on this level, on this scale, but imagine you have a shipwreck, 100 meters long, and you compound that. You can have meters of distortion in the photogrammetric record, for example, and that could possibly, I'm saying, misrepresent an interpretation of the shipwreck site. Could convert from a cargo. You could think it was a cargo ship, and maybe it's more like a 4-to-1, naval sailing ship. So, so that's the kind of thing we're looking at here. Finally, Dr. Irina Rossi's project, just a few days ago, was great to be invited on it. This is a Roman era 1 to 3 AD shipwreck located also in 3 meters of water, very close to shore, here near Nîmes. And the objectives here, we wanted to keep it simple because we didn't know how much time. We had a few days to work with, but achieve a 4 by 1 meter sector scans of the mast step in the keelson. That's where the mast goes into. There's a hole. There's a distinct hole, by the way, that you can see. Achieve sector scans of the entire keelson. If we achieve that, the whole wreck site, by the way, is 6 meters by 3 meters, so it was a nice, smallish site to work with. Achieve sector scans of the entire shipwreck site, if we could, and reference them all together. Analysis of the detail and reflectivity values as it pertains to submerged cultural resource preservation aims. Document timings, other observations, and comparisons of the laser scan to photogrammetry of the wreck site. The photogrammetry was also done, so this is a fantastic photo, which was just given to me by Dr. Kota Yamafune, showing the contrast of the wreck from our dive platform there, which was only a few meters away. And we did it, of course, we just, as opposed to other baseline scans, we didn't laser scan during the day, just tried to achieve the best results possible at night. There's another photo. That's the setup is very simple again. It's a laptop on a little dinghy, inflatable dinghy, which was fun. And that's what the entirety of the shipwreck looks like on the bottom. Of keen interest, features to this wreck, what you have are it's a stitched plank boat, which they're very rare in the record, and of keen archaeological interest as far as its construction and time period is concerned. And what the team did from the Zadar Museum was they put little tacks in each one of the stitch points. And these tacks, had varying degrees of reflectivity. They're metallic, yellow, some white. And so I was curious to see how the laser scanner would pick that up. And also, what I really liked was, again, there's a very strong, good, distinct geometric feature of the mast step up here. You get a closer look at it later. But also notice this wormwood here area, very distinct from the more well-preserved part of the keelson. So, want to get volumetric measurements of that, see how the laser scan would do that, and also hopefully compare to the photogrammetry later. Set up, this is what it looks like. We placed it about a ½ meter away from the subject scanned. Again, it scanned out about 1 meter. You get a 1 meter by 1.5 meter swath with this setup, 45-degree angle scan. And that's what it looks like, as you saw in the previous video. Again, credit Coda for this great footage of the scanning process. And what we were able to render was some nice stitched sector scans of the entire keel, and in particular the keelson with the mast step included. That gives you true geometry, as it turns out, of that. Very distinct, very nicely detailed. But also, as I was saying before, it was my hope that we would get millimetric precision of those individual stitch points, and we did. We did not get geometric precision. It didn't capture the exact morphology of it, but those are measurable now, and they're in perpetuity. You know, this is forever. It's a digital 3D data set. We can now view it in mixed reality, virtual reality for generations to come. You can now see at future dates how these degrade, how all of this degrades in micro-analytic terms. And here's a shot, again, of the wormwood. We did get accurate contours right down, determination actually right around 1 millimeter is what the data produced. So, overall observation, tentative conclusions. For maritime archaeological research, in a few cases, diagnostic features are either revealed or enhanced through laser scanning, which is measurable within 2 millimeters spatial accuracy, confirmed through the reference objects. More accurate spatial accuracies through laser scanning can create digital ship reconstructions, which can lead to higher levels of confidence in replicating their performance and extents that they could have, for example, traded to a certain extent, which is of keen interest to the maritime archaeologist. Within submerged cultural resource management, scalar reflectivity values can add a new layer of perspective, information, and therefore inferences of how A, diverse an assemblage of artifacts and features are present on a site, B, more confidence in site integrity and condition, and C, for tracking site formation processes. I think this is the strongest value of laser scanning, combined with, say, photogrammetry and sonar. Additionally, laser scanning can act as a spatial accuracy quality control, as I mentioned, for other means of 3D capture to provide the best data sets, holistic data sets possible to achieve the most archaeological site goals and objectives today. For SCRM, what I'm excited about as far as future potential is its incorporation with machine learning. Machine learning is involved in classification of objects. Pierre Drapp has done great work with photogrammetry, and he's observed, though, that photogrammetry can classify different objects, but edge detection is a problem. But laser scanning can resolve those edges, so positive returns of different classified materials are of great potential for use with laser scanning with machine learning. Its use within mixed reality, it can engage, it can excite the public. I think I was talking to one little boy from Biscayne National Park, and he's like, it looks like Tron, you know, like the laser scan. It's really cool, you know. So just from an artistic standpoint, people can take interest, engage with it, and learn more about their cultural heritage that way. Operationally, from a diver deployed standpoint, what I'd like to see is a tetherless solution. Again, if any marine engineers are out there who want to work with me, partner with me, we can make this tetherless, we can make it dynamically scannable, and it doesn't have to be just diver operated. It can be mounted, like I said, on ROVs and AUVs, speed up the scanning process, increase the scope of the scans, scan in profile at about 1 to 2 meter heights as possible, And additionally, telemetry. The telemetry can act as ranging for you ROV, AUV enthusiasts, control of the ROV in relation to the subject scanned. You can use the laser scanner actually to fine-tune control and ranging over the site, potentially, is what I've recently learned. And then testing. Many of the world's aquatic systems and sites can reside in variably turbid areas, so more tests are needed, I think, to find the borderline, the very limitations of how this can work in turbid environments. So those are subject of future case studies. I want to thank you for listening in, and sometimes I want to explain this. Sometimes you get to work with this cool technology, and in this case, this is we got to look at the more powerful ULS 500, which actually it can burn your corneas if you look at it too long. So you have to wear these visors. You're forced to wear this visor wear and sometimes feel like a superhero, in the case of wearing the same eyewear. Thank you very much. So.